Okay, hi everyone, welcome to lecture 2. So let's in this lecture let's continue discussing about this correspondence, and in particular the goal will be to derive this Cardy formula for line defects. So last time I wrote down this correspondence. And I told you that in order to establish this kind of correspondence between 3D gravity and statistics of 2D CFT, it's easier to do it in two steps, where you first show the correspondence between gravity and Liouville, and then use Liouville to derive the universal statistics or Cardy formula for the line defects in CFT. And I started giving an overview without getting into details. So I gave an overview of this part, overview of line defects in Liouville CFT, and how I sketched how you can use the dynamics of line defect in Liouville to determine the statistics of related line defect in 2D CFT. So now let me quickly give an overview of this part, and then we can get into some calculations of line defects in Liouville CFT.
So the statistics
Yeah.
was sort of coming out because you used this identity geographer.
Yes, correct.
But is there a more microscopic understanding of what kind of statistics, like what are you averaging over?
Yeah, okay. I guess there were questions about averaging last time. So I thought I'll just give a simple example for how you can make that formal average slightly more explicit by thinking of it as an average over certain coupling, like a marginal coupling. Yeah. I didn't plan to do it now, but maybe I will do it subsequently. Yeah. Okay, so bigger. Okay. Okay, so let me quickly explain how thin shell black holes correspond to line defects on the boundary. So recall this path integral picture that I drew last time. So where you can think of this as a plane or a cylinder or a torus, because you could do identifications on this side and or this on these two edges. And then what we are trying to compute is the 2-point function. So this is the path integral for the 2-point function, where I have inserted this line defect along this line. Let's say it's at minus tau naught, and this is at plus tau naught. I'm thinking that there's some coordinate system along this direction, and in that coordinate, the locations of the insertion points of these two line defects are at minus tau naught and tau naught. Okay, so. So the rule of ADS CFT is that that you fill in the boundary conditions described by the CFT path integral with a bulk geometry. So basically what we are trying to do is we are trying to compute this two-point function holographically using the by doing a gravity calculation, and ADS-CFT gives us a rule to do that. So the rule is that I have to fill in the boundary conditions described by this path integral with a suitable bulk geometry. Okay, so so with this being the boundary, so this sources a shell through the bulk. Okay, what is it? Sweet draws. Okay. So you should think of this direction as extending into the bulk. So
Shell of what?
a shell made of dust particles. There's no pressure.
This dust part. You're thinking of this line operator as being the integral over some.
Yes, you can think of this line integral, the line defect as a continuum limit of a product of local operators, and each of these local operators sources a particle of dust in 3D gravity.
And the local operators are all of dimension what?
All of dimension which scales with C, but small, going to 0. Yeah.
Okay. Therefore, like it's WKB.
Yeah. WKB, yeah, world line approximation.
So the dimensions are large enough that you can think of the.
Yeah, so the dimensions are large enough such that you can work in this WKB approximation and you travel along world lines, but they're small enough so that even when I consider the total dimension of a large number of particles, it gives me a finite number, which is the mass of the shell.
The top guy could join anywhere on the bottom, right? Is this some leading piece?
Top guy
Let's
could.
think of it as you said, as the limit of these lines.
Sure. Let me say that.
That means you also have these lines, specific lines there.
Correct. So that means this particle could go and join somewhere here. So
Different configuration.
that is a different configuration, but we can easily avoid that configuration by saying that these particles are secretly carry some quantum numbers, although they have the same dimensions.
A
Yeah.
lot of quantum numbers.
Yeah, you could say that they're charged under some approximate flavor symmetry.
So you have infinitely many symmetries in the problem.
No, I mean, I'm saying that in order to think of this as the leading configuration, you can just avoid those other configurations in this by just adding some other quantum number, so that the.
I'm just trying to see whether this kind of thing is natural.
Oh, I see. Okay.
You require one symmetry with many charges or infinitely many symmetries. I would imagine many symmetries for you to actually pin down a line. Right? Because if you had multiple charges with respect to one symmetry, they could just combine and go somewhere else. Maybe it's subleading.
Or do you like
Yeah,
extremization over possible endpoints? Start with one point. You extremize over one.
That's right. I mean, so if they're not charged, then if they're like completely equivalent, then you get all these winding configurations where this particle goes here, this particle goes here, and so on. So those winding configurations are expected to be subleading, because you can have such configuration even when you have like finitely many particles, but I mean, I don't have like a rigorous proof that it's subleading, but it's expected that it's subleading. But I'm just proposing like a very like a crude way to maybe avoid those configurations by like.
These are very heavy operators. I mean,
Yeah.
with C.
Yeah.
The one that where they connect point by point will be the. Then anything else will be.
Anything else will be subleading at large size, at large C. Correct. Yeah.
Because the lengths are large.
Because the length. Yeah.
And how many such? Are we imagine? Should I think of this as being, when you think of these particles? How should I think of this as being really a bunch of points?
Yeah.
And the number of points is not large compared to C.
Okay, let me give you the scaling. So then let's say the defect is made of n local operators, and I take n going to infinity, and each of these operators have scaling dimension h, which scales with C. But when I take h over C, that is small. So I'm taking n going to infinity, h over C going to 0, such that the product is held fixed, and this product is the mass of the shell.
N is the number of.
N is the number of operators.
Sorry, n goes to infinity and
H over C goes to 0.
H was what again, please?
H is the dimension, the conformal dimension of the operator.
But this makes sense for, let's say, some parallel.
Yeah, parallel. Yeah, I'm always assuming parallel configuration. I'm not.
You know, if you have interesting cross ratios, then what will happen in the bulk is a little bit of takes working out, right?
Yeah, it takes working out, and
This has to go to the closest one, then
exactly,
which
yeah.
among them is the dominant.
That's it. That's it.
Length sum to the small.
And moreover, you will kill the spherical symmetry of the problem. The reason why I'm working with parallel defects is because in the bulk, this gives me a spherically symmetric configuration of a shell. If I lose spherical symmetry, then it's a very hard problem. Yeah.
So NH over C is held fixed, right?
Sorry?
Any-
NH over C is held fixed. I mean, so actually there's a factor of 12. So if you, this is the mass of the shell. I mean, okay, you can ignore the factor of, it's not very important. But so this is the mass of the shell.
So H over C goes to 0, but still you're thinking of some geodesic.
In the large C limit. So you could say that I'm doing this scaling first, and then finally I'm taking large C, so that I can work in the WKB approximation.
And sorry, should I think of N as being roughly 1 over C?
Well, I mean, you could think of N to scale with C, but I don't want to do that. It's because there are some results which also work at finite C. If I make N just scale with C as 1, you mean C, right? Not 1 over C. Yeah. If I make N with scale with C, or say square root C, then at finite value of C, then there are just like finitely many operators. So it's not a line defect anymore. So.
Also, I think that if you scaled N with C, then there will be entropy effects.
I see.
For Abhijit's binding things, and you have to be careful.
I see. Okay. Yeah.
Yeah, it's not clear that this is dominant in this particular limit that you are also.
Okay.
I'm thinking like H large,
Mhm.
C large,
Mhm.
but H much smaller than C.
Yes, that's right.
Yeah.
That's right.
So I think you said that for H large you can use a point particle approximation.
Yeah, that's right. Yeah.
Right.
And N, I mean, it's clear. This approximation is clearest to me. If N is a large number, which has nothing to do with C.
Yeah.
Yes.
That's true. I'm not scaling N with C. Yeah.
And at minus tau naught there is the line defect that you
Yeah.
drawn. So basically this line defect corresponds to n number of operators.
Yeah. This. Yeah.
So d sigma where is specified like it's the operator on the boundary, some operator.
So d sigma refers to the curve on which I'm placing the line defect, and that curve is like at a fixed coordinate of minus tau naught. Like there's a coordinate in this direction, so the curve extends along that coordinate, and then there's a vertical coordinate.
Okay, so then you have told that something that you want to find some 2-point correlator on
Yeah,
two operators. So
this-
the operators only want to do the 2-point correlator that lies on the boundary. I mean the edge
This is a
operator.
boundary picture. Yes.
You mean the edge operator 2-point correlation or something?
So this path integral defines the 2-point function of the defect inserted
There is
at.
n number of operators on each line, right?
Correct. Yeah.
So the
It's like an infinite point function for the local operators. So it's a 2-point function for the line defect, but an infinite point function for local operator. Okay, so this was the boundary picture, and I was just trying my best to fill this in a way you can understand, but I don't know. Yeah. I don't know how to shade this, but yeah, you can.
So even this WCB approximation in the bulk, is this clear that some other bulk geometry may not dominate in the sense?
It will dominate. So I'm not saying that this is the only bulk geometry. I'm drawing a bulk geometry.
No, I mean even the one where two combine. So would it not be that, let's say you have two guys, the phi here and phi bar here, and then the thing that you are doing is phi going to phi bar here and phi
Yeah,
bar there.
correct.
But rather than that, let's say these phi combine here and become a singularity which is not so strong. So this propagation is like not so costly, and then it goes there, and then it splits into phi bar.
That's possible, but I'm assuming that they don't interact. So
No, this is a bulk geometry, right?
yeah.
So
I mean, if you're introducing a vertex, that means they're interacting. Yeah. Okay. Okay. So basically, this is one portion of the bulk geometry, and there's another portion here.
Sorry, but what does it mean that you are assuming that they don't interact? This is this is like OP coefficients, right?
Yeah.
Or heavy operators.
Yeah.
So one is saying that these OP coefficients vanish.
Yes, that's right. Because in the bulk, let me write down what theory. It's just the sum over world lengths of these particles. There's no interaction between the world lengths. There's just a sum of m times integral dl. Yeah.
Yeah, but I'm saying this bulk should model some reasonable CFT, right?
Yeah.
And this CFT, you already have some statistics of C, I, J, K, and all that, right?
True.
These universal
Correct.
statistics.
Yeah.
And you are here picking out those operators
Mm-hmm.
which somehow don't interact with anything, meaning their OP C, I, J
Mm-hmm.
is somehow 0 for all J's. And that seems like a very special choice.
Generalized mean field theory.
Yeah. Yeah.
Generalized meaning, yeah, but I thought this is supposed to be teaching us about some general things rather than a particular thing, namely generalized fields.
No, sorry. What do you mean by general thing? It's like a specific configuration in the bulk corresponding to thin shells.
I mean, saying this, if your approximations work only in this particular bulk theory, which is only free fields,
Right.
dual to a particular boundary theory, which is this generalized free fields, then it's not very general.
That's true. So, okay, regarding this OP coefficients, I don't think we have to assume that it's 0. All I'm assuming that the identity block dominates. So, I'm assuming that the OP coefficients are such that this growth condition is, the identity block dominance holds. That's it. I don't think I have to assume that they're exactly 0.
No, but identity block dominance will not rule out the kind of.
Yeah, so there are different channels you're talking about, because the identity block involves very different winding channels. So I'm not ruling out that possibility. Like it's
not
a
winding channels, but
yeah.
even these things combining and then propagating and then again combining with this fiber, that kind of thing. If you circle the whole business, still identity travels in that, because all of this is closed in one rectangle. Sorry, it may not be very important, but just wanted to get clarity about what is it that. So we are working with some general theory, right? When you say this line defects, you are writing down some general line defects.
Yeah, general line defects like
In some general CFT, right?
yeah, in general holographic CFT.
General holographic CFT. Yeah.
Correct.
So I guess then my question I would ask it, I guess.
You have in mind, for instance, where the shell from tau naught just doesn't talk to the shell from minus tau naught? Like
No. So let's say because this is built out of points, we can just look at the points.
Yes.
And it could happen that this pair of points which are next to each other in the first shell, they come close
Right.
and immediately source some other light particle.
Oh, I see. So the shell is made out of some other sort of.
Because this is some operator, right? Heavy operator, let's say phi. So phi O, there is a 3-point function. So now that helps me build a O in the bulk.
Yes.
And this O is light.
And then that goes in.
Travels, and then again it joins to fiber. And then you can imagine this process line by line, pair by pair. So instead of this kind of sheet, you get a kind of a half-dense sheet with mainly made out of O's.
So it's a shell of O's.
Shell of O's. I'm saying this is just one picture, but there are similar processes that could happen. Even this cross-talking, now that you have O, you could have.
This
I don't
can
know.
talk to something over there.
But let's see. So in the limit where the shells are very close to each other, I would just say that I can work in the identity block approximation that each pair of operators is just exchanging an identity, right? So you could say that there is that I'm working. So it's not true that for any value of tau naught this is the geometry.
They're far
So
separated.
yeah, when they're especially when they're far separated, the effects that you're talking about will become important. But there has to be a regime when tau naught is sufficiently small so that yeah.
So in particular when
Modulo and scaling issues.
Yeah, that's right. Yeah.
So you're assuming that when the line defects come close together, the identity block dominance is basically operators from these two lines coming.
Yes, just normal. It will become an infinite product of 2-point functions.
Right. But
Like,
what about the fact that you have a bunch of local operators on one defect itself? So there also there is an OP between.
No, that's 5, the charge, let's say.
yeah,
So 5 I don't go to identity.
yeah.
So but that's where something like what you are saying will come into play. Because not just it's the OP of those two operators that are coming together on the same line.
Yeah,
Right?
charge
Giving
two.
you this exchange.
No, but if they are very close, then perhaps, if the spacing is large and they are coming close.
I mean, it's an order of limits. Like if they're sitting right on top of each other, then they just it's just the identity that has to dominate. But there is some kind of a spacing in this direction, right? Yeah.
But I mean, it seems like the relevant spacing, the relevant question is how close versus how much
Yeah.
discretization is.
Yeah. I mean, if we assume that all the operators are identical, yeah.
For Abhijit's question,
Yeah.
because that's roughly the cross ratio.
Right.
So, I mean, I thought that, are you taking these things closer than the discretization?
Yeah, in that limit, yes,
Then
this works. Yeah.
But then this is really not a line operator in that limit.
It's not a line operator. It's a product of infinite product of local operators. Yeah.
Fine, so that's what it is.
That's
But you also want to have a range of tau naught where there are genuinely line operators, but still, those, I'm calling them geodesics, but those lines which are drawing dominant.
yeah.
So there's some
Yeah.
regime.
There's some reason.
That is far from clear.
It's not very clear.
seems like that tau naught will go to 0, right? If you then send up this discretizing like this.
It's somehow ratio of tau naught divided by the spacing.
Okay, let's see. So I'm saying that this is the identity block. I mean, because you should also remember that C is going to infinity, and when C goes to infinity, I mean, there are like very general arguments that identity blocks dominates for any correlation function. So, so I'm not saying that this is true at finite C. This is you're also taking C going to infinity.
No, but that also only if S channel is closer than T channel, right?
No, I think he's saying that every fusion is suppressed by 1 over n.
Yeah, exactly.
So if n is the largest parameter of the problem, there is no fusion.
Yeah, the n is the largest parameter in the problem. Yeah, that's right.
Right? Every interaction is 1 over n. Each particle is heavy, but not. This is what's confusing me. The particle, is it heavy like C? H by C when you say is 0?
It's not heavy like
It's one. It's because H C by n is order 1 number, and n is not scaling with C.
Yeah, exactly. It's heavy like C.
Heavy like C.
Yeah.
So then it's not clear that so much suppression, right? Because 3 Planck scale particles don't interact in a suppressed manner. I mean, the interaction.
This is H measured in units of C. Exactly. So these are massive Planck scale particles.
Planck scale particles, so then it's not
Like-
clear that the interactions are suppressed.
Yeah. Yeah, that's what. In fact, you can see that the explicit geometries,
Yeah.
at least when these are large, this geometry where these two combine and a light defect travels, just geometrically with the conical
Conical
deficit.
deficits, yeah.
This is dominant over straight line propagation of heavy defects.
I
I
see.
mean, he wants to get away from that by taking them close, which is okay, but then you cannot take n to infinity at some fixed tau naught, right?
I see.
Because then dominance will change, because that discretization length will go to 0.
Mm-hmm.
So as long as Shiraz discriminant is bigger than that tau naught, then you can see that similar things.
But is it clear that these two operators, like maybe like if they have if they are slightly different operators, they fuse to form some operator which I'm allowing in my bulk theory? Because I am writing down a bulk effective field theory,
You
right?
know, why are you writing the bulk effect?
Oh, I have not written it down.
No, I mean, it should, even in general CFT, right? In general CFT, you can have these 3-point functions.
Okay, I see. So, okay. Well, I'm just saying that I'm taking a CFT such that it admits these kind of shell solutions. So I don't know if you would say that's generic or.
And that may be a null set, right? I don't know. So I don't know. I mean, but we can move ahead. Yes.
Okay.
You know, this basic tension, that if you take n scaling like C, then there's all kinds of entropy effects you have to take into account. Then the particles can be light, but there's entropy effects you have to take.
I mean, would it be okay, like if n scales smaller than C? I mean, will those effects that you're talking about will still be important? Like n scales as root C, for instance.
Yeah, then you'd have to do a calculation.
I see. No, because this kind of scaling is, I mean, you could probably play around with it. Like you could say h goes as square root C, n goes as square root C, such that nh over C is.
That may be a equivalent.
Yeah.
No, but there is that, and then there is this tau naught also. Tau naught versus an issue also, right?
Yeah, but if he suppresses your fusions by interaction effects, by 1 over n's, then that would be very different.
Yeah, so this I don't understand, because at least for long distances, these are not suppressed. These are sometimes even dominant.
But if each particle is very light,
They are all Planck scale.
but now suppose he does something else.
Yeah. So let's say I do this. H goes as square root C, n goes as square root C.
Oh, I see.
Let's see. Yeah.
But then you don't have WKB approximation.
No, WKB works if h is large compared to 1.
Yeah.
Yeah. So that's okay.
Uh-huh.
So if he can go to some n, as he said, so that your square root Planck scale particles,
Yeah.
the square root number, and maybe then it'll work.
Yeah.
I see. Okay. So thanks for pointing that out. I didn't know that this would play an important role. But yeah, maybe this is a better scaling to work with. Yeah.
It would be worth estimating though if these entropy effects.
Okay. Yeah.
They go like some power generally.
I see. Yeah.
It would be worth estimating.
Okay. Yeah. Thanks. Yeah. Okay, as I was saying that this is a bulk geometry that corresponds to gluing, for example, a portion of BTC to a portion of empty ADS. So it's hard to see that from here. So let me draw another picture which is equivalent to that. So we know that empty ADS3 is a solid cylinder. So let me take an angular section of that solid cylinder. So this is like the origin of the polar coordinates, r equal to 0, and this is r equal to infinity. And now I introduce the trajectory of the shell here, like this, okay, and now I am gluing this to a portion of BTC. So BTC is a disk times S1. Since I am suppressing the transverse directions, so I am just considering the disk, and then there is a similar trajectory of the shell in the BTC case, and now what I am doing is I am deleting this part of the geometry and then gluing the portion of empty ADS to a portion of BTC across the trajectory of a shell. So the physical region is this plus this.
Oh, so the left is pure ADS?
Yeah, the pure ADS with say, let's say the global time is going this way, and on the right hand side this is the Schwarzschild black hole or the BTC black hole with the Schwarzschild time usually running. Okay, so this is the geometry that computes the 2-point function.
And the junction of these two.
And the way to determine the trajectory of this shell is by solving the Israel junction conditions.
And where the two boundaries meet, there's boundary there meets the boundary of the
Yeah, so the boundaries are this. So the boundary is this, and then it continues here, and then continues here. So it's like you start from the vacuum, evolve, insert a shell, then the shell propagates in the bulk, and then you annihilate the shell here, and then go back to the vacuum.
So your CFT is not at finite temperature, right?
I can do this at finite temperature where I have to glue two BTC black holes instead of gluing empty ADS to BTC.
And the idea of gluing it to a BTC black hole comes from the fact that you want the shells to collapse.
Yeah, I want the shell to collapse into a black hole, and that happens when the shells are sufficiently highly energetic. Like you can make the shells energetic by making tau naught sufficiently small, so they'll collapse into a black hole.
So in particular, there are solutions where the shell is outside the horizon?
Yeah, there are also solutions where the shell is outside the horizon. So here I've written a configuration where the shell is inside. There is also a configuration where the shell is outside. So that's an interesting geometry because it's locally a black hole geometry but without a horizon.
Right.
Yeah.
But that, so there's some critical mass or something which determines?
Yeah. There's a transition. I mean, you can say like so the transition occurs when the shell like exactly crosses the horizon. Yeah. So that's where the transition occurs.
And that's controlled by the mass.
That controls by the parameters like tau naught and m. Like you need to do yeah. So the inputs to this path integral are the mass of the shell and the landing parameter, what I call tau naught. Yeah. Okay. So for the non-rotating black hole, the general result is as follows. So in the semi-classical limit, the action of the black hole or the partition function would be e to the minus action of the black hole is equal to the 2-point function of this line defect, which is equal to the identity block and which is equal to the Liouville action. So these equalities would establish this set of relations.
I just missed this business with the black hole. Tell me again. So now the final boundary is that whole blue. It's just one boundary continuous.
Yeah, okay. Maybe if I draw it in this figure, it's clear, right? What is the boundary? The boundary is continuous.
Yes.
Yeah. So in this figure, maybe instead of drawing it this way, let me just draw it like this. Here is a shell insertion and here is a shell annihilation. So the boundary is here, goes here, and then comes back here. So this part of the boundary belongs to empty ADS, this part of the boundary belongs to BTC, and this part of the boundary again belongs to empty ADS.
Yeah, sorry, Shobita asked, but I missed, how is it that, I mean, why are we doing things like that?
I'll
that
prove.
picture there was the solution, I mean, the bulk.
Yeah, so that these two are equivalent because it's hard to see it from here, but this is the black hole. The region that is shaded in this color, this is the black hole. There's a horizon here.
Oh,
Yeah.
I see.
And this region outside is the empty ADS.
Black hole, but I thought these are very light guys, they don't back react.
There are so many of them.
I see.
This is number m which controls.
Yeah.
This, they will collapse.
I see.
This is a Euclidean version of it.
So the Vaidya limit is tau naught going to 0.
So the part nearer to the nearer to the boundary is the black hole solution. The part further away is empty ADS.
Yeah.
Yeah, so the region inside the shell is empty ADS, the region outside is the black hole. So the part which is closer to the boundary is the black hole. That is why, like if you if you compute the energy of this solution, it is determined by the black hole metric because the black hole is what is outside, right? So that the ADM energy of the solution is determined by the black hole.
I see. It's just accounting for the energy.
Yeah.
But now probably you would have to rethink all these scalings, whether they are enough to form a black hole in the middle.
No, he wanted that because his M was of order C. His final mass was always of order C.
Final mass is of order C. Is it of order C? I thought the mass.
Final mass was fixed.
Order C. No, final mass is just order 1.
Mass of the shell is
Of the whole shell. I think he wants the whole shell, the total energy to be.
total energy is energy is that of a black hole. So black hole has energy which scales with C. So the energy is so even though M is of order 1, the energy will scale with C.
It's a question of how you're dividing it up into various particles.
Yeah.
N is the number of particles you're dividing that full order C energy into. And then if N was order 1, not scaling with C, each particle is order C. But if N scales with C, then each particle is.
So can you repeat why the black hole was outside and this area was inside?
I mean this. How do I explain? Okay. So.
Lorentzian space, imagine you send a shell from the boundary.
Yeah.
Nothing's affected inside. If up to where the shell is reached, you just have untapped areas inside. Then there's a jump in energy and you see the energy. There's no energy inside. You make a Euclidean, whatever, Gauss thing, there's nothing inside, but it's there outside.
I mean, a simple way to see is you look at this figure and look at any instant of time where the shell is already present. Like for instance, between this time and this time, you look at a bulk slice, say this slice. So this is r equal to 0. It's not a boundary. This is the origin of polar coordinates, and this slice is hitting the boundary in the black hole portion. So that means the black hole is outside and the empty areas is inside.
It couldn't have been empty areas inside because you have to see the energy of the stuff. The boundary sees the energy.
Yeah, so if it was the other way around, the mass of the shell would have been negative. Like if for a positively massed shell, like it has to curve in certain ways such that the more energetic space-time is outside and the less energetic space-time is inside. Okay, so this is for the non-rotating black hole, and you can also add rotation. Like so these line defects can also source a rotating shell.
And this is not a minimum size from the MTAD's point of view.
This is a geodesic actually.
This is a geodesic.
So a geodesic is a particular.
Geodesics.
Sorry.
I mean, you started out.
Yeah. So the trajectories of the particles are each geodesics, and those constitute a codimension surface. That's the shell.
The shell itself is not minimal.
So
Individual lines along those.
It's a congruence of geodesics.
that's right. So by minimal area, would you mean like k equal to 0? No. K is not 0. No. Because k actually jumps, right?
No, but let's say from one side.
From one side, I mean from neither side, I think it's 0. Yeah.
And this is a geodesic viewed from both sides.
From both sides, it's
I think from the ADS side.
from the black hole side, it's definitely a geodesic, but I think it's also geodesic from the ADS side. Yeah. Okay.
So I'm a bit confused about the M versus ADM energy distinction. What?
M is the mass of the shell. It's like the local mass of the shell,
Yeah.
but the ADM energy is the energy of the black hole.
Energy.
So there's like a lot of binding energy.
They're
That
not the same, right?
yeah. M is small. E is of order C.
But ADM energy is.
Yeah, is of order C. So there's like a incredible amount of binding energy. Okay, for the rotating black hole, also the equivalence holds. So this is a much harder calculation.
I'm not sure that I understood this. M was mass of one particle or
Mass of the shell.
Oh, then I'm totally sorry. The mass of the shell is not same order as sum of masses of all. I mean,
It is of the same order. Yes, correct.
then
Sorry, but M is order 1.
No. So what I'm calling as the mass is like this quantity. Okay, maybe you can call C times M as the mass. Okay, sure. Yeah.
wait. Can I just suppose there was no interaction energy.
Okay.
I just took the energy of each
Right.
operator,
Right.
each particle, whatever.
Right.
Then would I add it up? Would it add up to C or not?
Yes. I mean, NH is the MC. Right?
Yeah, NH is MC.
Then
And
So sorry, maybe I should have called this as mass parameter. Okay. Yeah. Sorry. Yeah. Okay. For the rotating black hole, the action of the black hole is also equal to the 2-point function but twisted. So you twist the 2-point function by introducing a rotation generator.
Oh, by mass you mean like a GR mass?
Yeah. Right.
It's just a scaling by C.
Exactly.
I'm
Yeah.
sorry.
Yeah. So this is also equal to the identity block, but now evaluated at a complex modulus. So that was was evaluated at a real modulus tau naught, and now this will be evaluated at a complex modulus, because now what you are doing is in the path integral you are introducing a relative twist between the two defects. So let's say you are moving this line here, a little bit relative to this. So now the trajectories will how do I say it? It will be slanted like this.
Why do they want to slant?
Because
The nearest crystal?
yeah, I'm going to their corresponding partners, like the operator and its conjugate.
But I suppose I just ask which way of joining if I didn't have many symmetries.
Well, again, I guess we can again go back to that problem. I'm assuming that though, like these operators can only fuse with their corresponding partners.
So it's like marked points.
Yeah, the mark points. Yeah, exactly.
So the lower points are the ones which are obtained by rotating your thing by.
I mean, I don't know. You can do it either way. You can push the upper points or you can push the lower
Yeah,
points. Yeah.
Whatever.
Yeah.
There's a relative.
There's a relative twist. Yeah.
Sorry, I missed the first line. Even can you say so? From all this discussion, what was this conclusion?
So the conclusion was, I mean, I didn't prove this, but I'm saying that if you compute the action of this black hole,
Okay.
this is I constructed a like a proper geometry for you. You can compute the Einstein-Hilbert whatever action
And there is a contribution coming from the sheet also.
everywhere, like everything. Yeah, the total contribution, and so that will be equal to the 2-point function, which is equal to the identity block, and which is also equal to the Liouville action. Appropriate Liouville action. So that establishes those three.
The Liouville
And this
action for
Liouville
what?
action has a source.
Huh?
The Liouville action also has a source.
Yeah, the Liouville action is defined by this non-conformal defect that I introduced last time.
Sorry, so that operator, what it does is that moves points along the defect.
Yeah, that moves points along the
Just
defect.
like pushes them away.
Yeah. So let's say there's a mark point, and then the mark point moves under the.
So if they're identical, it does nothing, right? Like it's-
No, it don't do anything. Yeah, so if all the operators are identical, then that will have a like a trivial effect. So so this is the reason why I want to make the operators distinct, so that I can talk about a rotating black hole in the bulk. Okay, is this part clear? Okay. Okay, so this is as far as the black holes are concerned. Both we can get both non-rotating as well as rotating black hole. Now, importantly, you can also get wormholes from the statistics of these line defects. Okay. So the simplest illustration that I can give you is the following. So consider a wormhole which looks like this. So let's say the boundaries are two spheres, and there is a line defect which wraps the equator of this sphere here and as well as here. And then in addition there are these spheres are punctured by local operator insertions. Okay. So now I construct a bulk geometry that joins these two boundaries. So this line defect will source a shell which gets annihilated here. So let me draw that like this. So this is the trajectory of the shell, and then these local operators will source world lines, matter world lines.
So
Okay.
now you have this picture, except that one of the line defects is on the other boundary.
Yes, yeah, correct. Okay.
So it's not, you're not talking of a single CFT.
It's not single CFT. It's there are two copies. Yeah.
Two CFT.
Yeah, because the goal is that wormholes compute multi-copy observables. Like here in this case, they compute averages of 2-copy
And
observables.
you're going to explain why
Yeah.
the two line defects are a non-trivial connected correlator?
Because of the existence of a wormhole. I guess if you are asking again from the CFT, okay. Again, it goes back to the question of averaging, and I'm going to discuss explicitly how, like I will introduce a coupling, and if you average over that coupling, it
Okay.
introduces a, okay. I think.
Suppose the operators on the first side had charge 1, each of these, and the operators on the second side had charge -1.
Okay, good. Yeah.
So they can connect to each other.
Correct. Yeah.
But within a given CFT, This correlation function would just be
Yeah, very nice. So, okay, I was about to get to that, but yeah. So that's that's related to global charge violation in gravity. So, okay, that's I'll just get to that. Okay, so what is this computing? On the left hand side, it is computing this matrix element. Let's say this operator is I and this operator is j, and this is the line defect d sigma. So it's computing this matrix element on the left hand side, and on the right hand side, it's computing its conjugate. So j d sigma dagger I mean conjugate just because of this orientation reversal going from right to left. Okay, so this wormhole is a contribution to this product, and in particular its contribution can be matched by doing an average. Okay, again this is a formal average as I discussed last time, but you can make it explicit by averaging over by introducing a coupling in this theory and then averaging over a small window around the couplings on both the boundaries. Okay, I'll get to that. That model I'll discuss it next time. I mean in the last lecture. But for now, like just take that this is a formal average. Okay. And if you actually compute the partition function of this wormhole, and it actually matches with the Cardy formula. So the Cardy formula was a function of these two operator weights as well as the mass of the shell. So this equality is just Cardy formula, that the line defect statistics is given by universal function, and then this equality is a gravity calculation. So this is CFT, sorry, not this is CFT. Okay, this is CFT. This is gravity.
The last line is the Liouville guy.
Yeah, this is actually the Liouville structure constant. So, yeah.
So this middle bar thing you are going to explain later.
This bar, right?
Yeah.
Yeah.
so this algebraically was a miracle, you think? That this somehow could you see before you did the calculations going to work?
I don't know. I would say it's some. I mean, for this particular case, I mean, because we already knew that for local operators this was true, right? For local operators, the OP coefficient statistics was governed by this wormhole.
Yeah, so let me ask about that.
Okay.
Was that an algebraic miracle? I mean, until the last step, last factor of 2, you weren't sure it was going to work. Or you
Yeah.
somehow knew that it had to.
Let's see.
What is equal to what was the question?
That the fact that the partition function of this wormhole geometry is given by an observable in Liouville CFT. That this is given by Liouville structure constructs.
Or it was given by what Maloney and friends found for this Cardy form.
Yeah.
No, but what is the meaning of that right hand side?
What is the meaning in gravity?
No, CFT.
In CFT.
CFT, it's a number.
In CFT, it's the
It's a bar, right? Some coarse graining, right?
Yeah, there is a single
CFT.
CFT object.
Yeah.
And so cost grading is just cost grading in energy.
Energy.
That's very
window.
clear.
Yeah.
It's got as clear meaning as a partition function.
Yeah.
Yeah, so Cardy and friends, Maloney and friends could prove theorems about it. Very clearly. Yeah. So
Okay.
this is somehow the key thing, like it keeps
Yeah.
written that this is equal to that.
So you're asking like what was the intuition?
I mean, what I wanted to know was,
Yeah.
was it like that you could see this part is that or something?
Well, all I could say is like I was the one who did this calculation, so for me it was a miracle.
For you it was a miracle. That's what I wanted.
Yeah. Okay.
One comment when we were chatting the other day. So from the gravity side, the right hand side I think is I mean if you just do it in a single copy CFT, it's a calculation with genus 2, right?
It's what?
Calculation with genus 2 surfaces.
No, you could do it in different regimes. So like I think we discussed that. So you could on the CFT side you could either compute a genus 2 partition function, or you could compute a sphere 4-point function or a torus 2-point function.
Wait, genus 2 and the moduli space, the H's are encoded where in moduli space you compute.
Yeah,
These
so
three
exactly.
Yeah.
Exactly, that's what I was about to say. So that you have a genus 2 partition function, and then you have these sphere with these lines
Mhm.
passing through, and then as you make them bigger, they kind of punch the
Punch the
holes.
holes as we
discussed.
Okay, good. So that
It's the statement that it's analytic in the
Yeah, correct.
analytic
Weights.
in the
Weights.
angular deficit.
Yeah, yeah.
Ah,
The weight.
so at one point it's just angular difference. It's
Correct.
just conical difference.
Yeah.
Then you put the whole punch in.
Yeah, that's
Yeah.
like a
Just
conical,
passes.
extreme conical defect is
Yeah.
a whole.
Yeah, yeah, yeah.
Yeah, so what would happen is that like when you make this the defect go above the black hole threshold, it becomes a hole that joins these boundaries. So now it's no longer that the boundaries are distinct. So you see now this resembles the plumbing construction of a genus 2 surface.
And genus 2 is what is used by Cardy and friends to compute.
In one regime, yeah, in one regime.
But then it's all analytic.
It's all analytic, yeah.
I see. So then it's less of a miracle, I think. Thank you. Yeah.
Okay.
Okay, fine. Okay.
So I think can you explain why it wasn't a miracle?
I think Abhijit should, but I'll tell you what I understand. What Abhijit just explained was that, you know, these lines, if you think of them as conical deficits, now if you take the mass of each of these conical deficits above the black hole threshold, then you should think of this conical deficit as being eaten out into a hole. Okay? And then it becomes like a genus 2 surface. Okay? But genus 2 is exactly the surface that Maloney and friends used, its modular properties of that, in CFT to make
No, but what is the miracle is the following, like even if you make this heavy, it becomes a genus 2 surface on the boundary, and then you are filling that genus 2 surface with the bulk geometry. But the action of that is not this. So the action of that is the identity block. So which you expand in this dual channel, this is the kernel. So somehow this geometry strips off the block.
no, of course, it's very non-trivial.
Yeah.
But it's just that there is some connection.
Yeah, no, yeah, of course, yeah.
That helps.
If it doesn't take too much time, excuse my ignorance. So what does Maloney et al. Show for genus 2 surface, CFT or genus 2 surfaces?
I think Jivan should tell us.
Yeah.
So what do they show?
How do they get this Cardy formula for
Yeah.
Cardy functions?
Okay, you don't have to go to genus 2.
The averaging over delta E, you know, where does that enter in that derivation?
I mean that is not very explicit. That's like microcanonical averaging. Like for instance, like the usual Cardy formula. How do you derive
So
that?
whatever it is,
Yeah.
I mean, you get an expression
Yeah.
in your statistical mechanics,
Yeah.
which depends on your delta E, which is your microcanonical window. Okay, and then what do you do with this expression? Now, what are you averaging over different values of delta E, or?
No, I think you get maybe a canonical expression, and then you do inverse Laplace transform to get to the way you go
Exactly,
from
yeah.
the high temperature behavior of the partition function to the Cardy function.
Fair enough.
And then
Yeah.
that already gives you kind of some sort of average answer. So here also you
Yeah.
use S-duality of genus 2 surface to map the code. I don't know which identity block, which channel, and so on.
Yeah, yeah, yeah.
Identity block in some channel where very heavy CIJs contribute,
Mhm.
right? And as a function of cross ratio is what you will get, and then you have to make an inverse Laplace transform to extract out the microcanonical answer, giving you some integrating.
But in that answer, does the resolution appear?
No.
Disappears.
No, it disappears because what you are actually computing is the average. So let's say you are doing an average over energy windows E1 E minus delta E to some E plus delta E, some dE times some reasonable function to average over, but the size of the window has to be sufficiently small, and then you are again dividing by this times whatever, and then again you are dividing by this. So for any reasonable function, it should not depend on what the value of f
This
is.
is like what happens in thermodynamics.
Yeah, thermodynamics. Yes, yeah.
You know, Shruti Pal and friends, for just a pure Cardy formula, have this very, very concrete analysis. They ask, if you just do an inverse Laplace transform and get a row of E, and then you compare it with the actual density of states smeared with some smearing function.
Mm.
Okay.
And as a function of the width of this smearing function,
Yeah, yeah.
when do these two things come near to each other?
Okay, so that should determine the size of the smear.
Yeah.
Yeah,
So
yeah.
if the smearing is too small,
Yeah.
these two things differ very much.
Yeah,
Okay.
right.
The smearing has to be large enough for these two things to be near to each other.
Okay.
And there are theorems about this, you know. And you can ask, what have you missed in the Cardy form? Well, you missed all the modular transforms of the excited states.
Yes.
Right.
You take only the vacuum.
Yeah.
You have to put all the other things in. All those give you corrections. But when the smearing function is broad enough, those corrections are not important. Okay, so it's very concrete analysis in that context.
So this is like thermodynamics.
Just thermodynamics, it's the same thing for the CIT.
Okay.
Just
But it will be more complicated to do such an analysis like what Srideep did because of the complications.
For this, it would be more difficult.
Yeah, because in the CADI formula, have explicit formulas for the fusion kernels and stuff, for the blocks and stuff. But here there is no explicit formula for for a block. Although it's quite interesting that the blocks do not have explicit formula, but the fusion kernel that transforms the blocks into one another has explicit formulas. So it's
Yeah, but you have-
So you only needed the form of the blocks in this limit where.
yeah, but I guess the point is to make this rigorous, right? Like what am I losing out? So if I should know what I'm losing out, I need more information.
Yeah.
So there's this application of Tauberian theorems.
Yeah, exactly. The Tauberian theorems will make this more precise. But I think it will be harder to apply the Tauberian theorem to this setup rather than Srideep's setup. Yeah.
Yeah, to get numbers it might be harder, but I have the feeling to get order of magnitude estimates for this.
No, yeah, of course, yeah.
I mean, the case would be order, same exact.
Yeah. Okay. Okay, I guess let's discuss the point that that Shiraz just brought up. Okay, so now I'll consider the special case where there are no operator insertions. So just it's like a two boundary wormhole where there is a single shell which is going across, nothing else. Okay. So what this is computing is the vacuum expectation value of the defect on this boundary times the vacuum expectation value of the defect on this boundary, conjugated average of that. So this is a very interesting expression because this defect could be charged under some global symmetry. So if it is charged, that means if you do this calculation in an individual CFT, this is just going to give you 0. But then because of the presence of wormholes, like this charged shell can find its partners on the other boundary. So it can go across and then get annihilated on the other boundary. So this is an example of the observation that wormholes estimate global charge violating amplitudes in quantum gravity.
Oh, right. You're saying the fact that there is no view.
Yeah, in fact that we know that at least we believe that in quantum gravity there is no global symmetry. But then let's say there's some kind of an approximate flavor symmetry in the low energy effective theory. So you should tell me how does quantum gravity remove this global symmetry? So the presence of wormholes in semi-classical gravity is a window to understand how global charge violation.
Suppose it was gauged in the bulk.
I'm not assuming that it's gauged in the bulk.
Suppose it was for a moment, then then there should be no violation.
Yeah.
And we see that this is also 0. Sorry, there's something.
Sorry, I mean, why is it not always gauged? I mean, if you have a global symmetry on the boundary, that should be gauged in the bulk, right?
Let's say there's an approximate global symmetry of the CFT which is not gauged in the bulk, like for instance some kind of a flavor symmetry.
If it was gauged in the bulk, it would be a genuine.
It's a genuine global symmetry. Yeah.
He's looking at something that looks like a global symmetry also in the bulk.
Yeah.
And therefore it's not a real symmetry. Like charge scalar field in the bulk, but not coupled.
Exactly.
Not coupled to
Yeah.
anything.
Yeah.
Not
Exactly.
coupled to
Yeah.
anything. But suppose it was gauged. Suppose it was gauged, then we have a paradox or not? Or there's some Gauss law or something that I have the feeling Dan Harlow would love this.
Yeah. So you're saying there might be some Gauss law preventing this wormhole?
I was wondering. Otherwise, it sounds like
yeah.
two things that are exactly 0.
Yeah.
You take the product and you get something non-zero. So
But the thing is, maybe this exactly 0 might be a thing of concern, right? Because these are some random. These have some randomness. But then when you average over them, you get a non-zero value. It's like mean being equal to 0, but the variance need not be equal to 0.
In each theory, let's say you had an HYK. In each theory, it would be 0.
Well, that's a very precise theory, right? But what I'm doing is like an effective theory. So I don't know in what sense I would say that.
Average over an ensemble of theories, each of which have the global symmetry.
I see. Yeah. Then I guess then you should find a way to
There should be some Gauss law.
There should be some obstruction that prevents this wormhole. Maybe if you gauge the symmetry, maybe such wormhole does not exist. Yeah, but I don't have an argument for it. Yeah.
Maybe if the weak gravity conjecture is obeyed.
Yeah, if the weak, okay. Yeah, maybe, okay.
Yeah, maybe it changes shrinks it to 0. Of course, if it's not obeyed, then you can make it gauge it arbitrarily weakly and it won't change it.
Right. Okay. So this is the statement. Now the other interesting part is this is actually the vacuum expectation value of the Liouville defect. So what you are observing is that the G function or the vacuum expectation value of the Liouville defect is what controls estimates the amount of global charge violating amplitude in this setup. And the reason why it could be interesting is because G function is related to RG flows. So maybe there's some relation between this global charge violation and RG flows. Okay, that's speculative. I don't want to
explain. Is there independent corroboration of this? That this is a good estimate of the global charge violation in individual CFDs?
How would one try to do that?
Maybe find a black hole with Hawking radiation violating effect or something. People have these words, right, for why global charges are not preserved because Hawking radiation violates.
Oh, so you're looking for something along those lines? I think those kind of
some other estimates which will give you the same thing with the same number.
But just from the bulk, wormholes give an estimate, right?
That's
this, right?
This.
Yeah.
I mean, this is like a concrete function. I can write it down.
Very, very concrete and very specific.
Yeah.
Now, this you've done some two boundary calculation.
Yeah.
I was wondering if there was some one boundary calculation one could do to estimate this.
Well, there is a one boundary calculation, but involving higher topologies. Like for instance, what you could do is you could take a black hole and then glue a handle into it. I mean, these kind of calculations are like routinely what the people in JT gravity do. So even in that setup, you can estimate like a global charge violation.
Yeah, but I'll tell you what I had in mind. Something more simple in mind. Yeah. In a Lorentzian setup, this guy creates this particle, it disappears into a wormhole.
Right.
In a black hole. And then the black hole radiates a particle with a different global quantum number as Hawking radiation, and then that saturates the function.
I see.
This one could, I think, physically estimate.
I see.
And I was wondering if you...
Yeah, I mean, that will be very hard to see like how that could be related to this number that I'm calculating. Maybe because it's a completely different process, right?
It's a different process. So that's not the mechanism required. How in a... Do you have a suggestion for how in a single boundary theory, what is the mechanism for the global symmetry violation? How does it happen? You're following the process, how does it happen? I thought the general feeling was that it happens through black holes, roughly along the lines of what I said.
Yeah, I mean, roughly the presence of wormholes is also tied to black holes because so remember that these were shells which were heavy enough to create a black hole, and I'm looking at a wormhole contribution corresponding to those shells. So secretly there's a black hole in this discussion.
Correct. So then maybe that same black hole. It's Hawking radiation could. Anyway, that's stupid.
Shiraz, maybe your mechanism, if I think of it in the eternal black hole situation, that some charge goes into the black hole, goes to the Einstein-Rosen bridge, and appears in the asymptotics on the left side.
Appears in the asymptotics.
So that may not be too different from appearing on the right side. So therefore, it may
just be the same.
Yeah,
excellent.
This is the kind of stuff that Subrat keeps saying, right? Whatever appears on the left side is not too different from what appears on the right side.
Excellent. I think that sounds very good.
I see. Okay.
Of course, all this is Euclidean somehow.
Yeah, this is a Euclidean two-boundary calculation. But I think what you are talking about, the Einstein-Rosen bridge is like
yeah. But this could be a t equal to 0 slice of
It's a t equal to 0 slice of one higher dimensional black hole. Yeah. Okay, so this summarizes like the entire part of my talk. I mean, the next part is like the technical part, like calculation. So I think it can go easier. Okay.
such a wormhole would exist for gauge charges, let's say, which are actual global charges of the CFT, then that would put constraints on what kind of ensemble average
Yeah.
is proposed, right?
Yeah, correct. Yeah.
Right.
That's
So
right.
you shouldn't, somehow having to do with global symmetries.
Correct, correct.
You cannot have an ensemble that also preserves symmetry.
So in particular, Witten's proposal.
This is Stanford and Witten. So basically, like in the context of JT-RMT, so they looked at the effect of adding discrete symmetries on the nature of the ensemble. So the nature of the ensemble changes. Like for instance, it changes. It could be a different universality class. Like if you have like a GOE ensemble, then you add like say parity or time reversal or whatever, it could become like another ensemble.
No, but Abhijit has a much simpler point. He's saying if your ensemble is in theories that preserve the symmetry, and your insertions also have definite quantum numbers, then the left hand side is just zero, right?
Okay. Yeah.
So then there should be no fluctuations.
Yeah.
So if this is an ensemble average, it would then have to be an ensemble of something that violates one of these conditions.
Yeah.
But that sounds, I feel it's much likelier, it would be much nicer if there's something in the bulk that prevents this.
Maybe in GT or RMT context, one can ask this question. Maybe consider RMT with some charge.
Yeah.
Right?
Yeah.
And then you consider two such things. And clearly, all the theories in the ensemble have that.
Yeah.
Right?
Yeah.
And now see whether there is a phi to phi bar wormhole in the JT
Right.
case.
Yeah.
What would that, if there exists one, then what would that mean?
So I thought I thought what we want to find is like how do we prevent that wormhole from existing, right? Yeah. So I don't know.
But it could be that the weak gravity conjecture is relevant. Because just in his context, if you now add gauge fields, that back reacts on the geometry.
Yeah.
Okay, but how much it back reacts depends on the coupling to the electromagnetic coupling. So if it's large enough, it could back react enough to destroy the law.
So
and maybe it would be really cool if that large enough was exactly weak gravity.
So you're assuming that the particles.
Continuous symmetry, right? All this is about continuous symmetries.
Yes, for continuous.
But his point could be made for discrete symmetries also.
Yeah.
Discrete, gauged discrete symmetries.
Well, I don't know what is in the bulk, but on the boundary you have global discrete symmetries.
Like a Z2 symmetry. Yeah.
Then what would we start?
Good point. So that thing is gauged then in the bulk.
Yeah.
Somehow. It's gauged because it's part of diffeomorphisms or something.
Yeah.
What could we do? I don't know.
I mean, there's a recent work by Harlow. I don't know if you have people. I've not like gone through it, but it was about gauging space-time inversions in quantum gravity. Something like that. Yeah. It seems relevant. Yeah.
So you're saying if there are gauge symmetries in the bulk, then there should not be a black hole because from this the gauging argument it seems that the individual terms should be zero. Is this the
Yes. Yes, because if the ensemble is done over an ensemble that preserves the symmetry, and you're always inserting operators of the same charge in some unreasonable, then in every element of that ensemble, this is just zero.
It could well be that there are no on-shell amplitudes like that. As you say, the back reaction pinches on this wormhole. But then I don't know about off-shell wormholes, right?
Off-shell topologies.
Yeah, it would be more satisfying if it was a Gauss law instruction.
Yeah. It's not like a.
thing sounds like an on-shell.
Yeah, I agree. Maybe something more general.
Okay.
One less thing to think about.
Well, then you'll also have to tell me like how like the page curve is restored and all that. If you Okay, let's go into detail of each of these topics. So first, let's start with one. Okay, so Liouville CFT is defined by the path integral. Where the Liouville action is given in terms of this Liouville field phi is by the following expression. Okay, so this is not the most general form of the Liouville action because I've taken the background metric to be flat. So this is just like a free field theory, the kinetic term of a field with an exponential potential. That's it.
There is something del bar or something?
Del bar, I mean, this is in z bar coordinates. So this is grad phi squared. Yeah.
And the pi is a
Phi is sorry?
product sign or something? This exponential sign.
Only 1 phi.
There's a product.
Pi or product sign something.
Oh, sorry, pi mu. Mu is the Liouville cosmological constant. And B is the Liouville coupling. So recall that the central charge of this CFT is given by this expression in terms of the Liouville coupling. Okay, so so this theory has some really special properties, and it has been solved completely by some very nice works of the Zamolodchikovs mainly. So the spectrum of this theory on S1 is continuous. So that's why it's called a compact. It's called a non-compact CFT. So continuous above threshold. And there is no vacuum state for this theory. So so the spectrum is continuous above that threshold with no vacuum state, and the spectrum only consists of scalar Virasoro primaries.
So you're thinking of the Liouville actually really as a theory of gravity, so...
No, it's not a theory of
2D gravity.
Theory of
So
2D
all the
gravity.
physical states are primaries.
Well, if you think of it as a theory of 2D gravity, then shouldn't you also like find a way to cancel the anomaly? Like you need the total central charge to 0. So yeah, I mean, if you're talking about Liouville, there's something called Liouville quantum gravity. So where you couple the Liouville action to some, say for instance, the minimal model in the CFT. So that cancels the total central charge and sets it to 0. So you need to, like, if you think of it as a two-dimensional quantum gravity theory, then you have to find a way to cancel the Weyl anomaly.
Well, you don't need matter really, that you could just add ghosts. Because
No, ghosts have a fixed central charge, whereas this is.
you need a matter to, B is determined by the central charge of the matter.
Yeah. So, like, if the central charge of Liouville is CL, and the matter sector should have central charge 26 minus C.
But just continuing Rahul's question, are we imposing physical state conditions or not? Is it just sort of a
That was my question.
Physical state isn't like
Are
what
we
is it?
demanding that states are annihilated by L0 minus 1 and L0 bar minus 1?
No. So that you would impose in like a world sheet theory or in a theory of 2D quantum gravity, but this is not a theory of 2D quantum gravity. Yeah. This is just a CFT. Okay, so the external operators could be I said that the normalized so the spectrum of normalizable states only consists of states above this threshold, but the local operators, the external operators, which you call vertex operators, could also be below the threshold. So these do not correspond to normalizable states in the theory. And notice that this threshold is also the threshold, black hole threshold in 3D gravity. So that's one nice connection. So the local operators are exponentials of the Liouville field. So these are scalar primary operators with parameterized by this alpha parameter, and they have the scaling dimension given by alpha times q minus alpha. Okay, I guess I didn't write what q is. So q is sometimes called the background charge and is given by b plus 1 over b, where b is the Liouville coupling.
And these are the only allowed external operators? I mean, are there also local or external operators got a dual to the states?
Yeah, because those states, I think they create like holes in the big holes.
So those are not local operators.
Yeah, I guess in that, that's right.
Which states?
Dual to the propagating states.
Yeah.
Oh.
So the propagating states is like b plus I k, right? Alpha is equal to b plus I k or something.
Alpha will be complex, yeah.
Yeah.
Oh. So there's no state operator corresponding.
I mean, the operators that you calculate correlation functions of are not the same as the things that make states. Right?
I mean, but you can also compute the correlation functions of these operators above the threshold.
Above the threshold?
Yeah, so they're given because all of these results are controlled by analyticity. So, so you can always keep pushing alpha to be given complex.
Threshold is the C minus 1 by.
Yeah, the threshold. Black hole. Okay, I don't want to call it black hole, but yeah. Okay, so for our purpose, however, we only want to study this line defect.
So, and just to remember from long ago, what the argument I used to read 30 years ago is that the operators that lie above the threshold actually create a hole of very big size measured in the physical metric.
That's right.
Macroscopic
Loop operator.
And so don't deserve to be called local operators. Is that does that play any
Those
role?
are the physical states.
Yeah, I don't think it plays any role in the discussion.
Okay.
Sorry, so what are those physical states as? I mean, is it easy to understand what they are as operators?
Yeah.
No, you can write down them as they're just of this form where alpha is
Alpha becomes
No, I think you are asking about the macroscopic groups. They are exponentials of integrals over a curve.
I was just asking about the continuous.
Oh, I see, okay.
exponentials of integral over a curve. This is the line defect. Okay. Yeah. Okay. Maybe you call it a loop operator, but I just call it a line defect. But okay, maybe it's terminology.
When sigma is closed, I mean that's like a
Sigma is closed here.
Oh, it's closed here.
Yeah.
No, it would be. I was thinking of more like dn e to the phi. So it's like a.
Oh, integral e to the phi. Okay. Yeah, that.
Phi e to the b phi or something.
Yeah. Okay. Yeah. Sure. So that is another type of line defect, but okay, you would call it a loop operator, fine.
No, it's in that sense that the physical size of that thing
I
is
see.
not finite.
Yeah.
Actually, from those Seiberg notes, there was this
Yeah.
idea that the physical size is like e to the power minus phi, right? Because e to the power minus phi is the metric.
Yes, right.
Okay, and therefore these guys, or maybe plus, maybe I get the sign wrong.
Plus. Yeah.
So these guys decay where physical size blows up.
I see.
Okay, so they have no overlap with finite size holes.
Right.
Whereas the normalizable guys don't decay.
Right. True.
That was roughly the.
Yes.
But I'm not sure. Those are all words, and it was not ever clear whether it would play a role in the mathematics of the theory. Maybe you're saying that.
And what are you looking for?
Looking for whether these operators will obey the rules of local operators.
I see.
And you're
Okay.
saying they do, right? You see,
Yeah. Everything is analytic, like for all values of alpha. Yeah. So the dynamics of these non-normalizable and the normalizable states are controlled by the same function, which is analytic.
Yeah.
That's it.
Yeah, I think that Seiberg would have expected that these normalizable guys would not behave like local operators.
I see. I guess that was classical Liouville, right? But I guess there was. I don't know if it was pre-Zamolodchikov's.
It was well preserved.
Okay. Then yeah, the modern Liouville is Zamolodchikov's Liouville.
Yeah.
Yeah.
So what is your aim? Sir?
Huh?
What is your aim? M over 2 pi.
M is the like parameter. The M is like the mass parameter of the defect.
Okay. And you are line integrating over sigma is the boundary of.
Yeah. So you can write this as a product of local operators in the limit n goes to infinity. So limit n goes to infinity of vertex operators of that type, where alpha would be m times the length of the defect divided by 4 pi times n times b. I mean, you can roughly see why this is equal to this, right? It's because it's exponential, and then the product of exponential becomes a sum. Yeah. Okay.
And what is it? Elsinger signifies physically? Something significant?
Physically, I mean all these properties. I don't know. Yeah. Okay. So this was about the quantum Liouville theory. So, but for our purposes, we only care about classical Liouville theory. So we are going to take the classical limit from now on. So we work in the limit b going to 0, which means c going to infinity. So in this limit, you can write the quantum Liouville action in terms of a classical Liouville action, where the classical Liouville action is of this form. So this field phi was not the same as the phi that is there. It's just a rescaled version of that. So this field phi is related to the quantum Liouville field by rescaling. Okay, so what are the equations of motion of this theory? I mean, I think you can just see, you can write it down just by seeing, right? So this is known as the Liouville equation. So this governs the theory of hyperbolic surfaces. Theory of hyperbolic metrics on surfaces. Yeah.
So you should think of left hand side as curvature and right?
Yeah. So this equation is nothing but r equal to minus 2.
Multiplied by e to the power minus 5.
Yeah.
It's 2D.
Yeah, 2D hyperbolic surfaces. So this condition is a constant negative curvature, and so the metric on the hyperbolic metric on the surfaces in conformal gauge is written in terms of the Liouville factor e to the phi times mod dz squared. So in a sense that Liouville theory is governing the dynamics of this factor. Okay.
So now you are really thinking of it as the theory of gravity. No?
Why is there gravity? Why is there gravity here? I don't understand.
Well, e to the phi is the metric.
Okay.
Our metric. So you're integrating over phi, so it's the theory of gravity.
But the theory is defined on the flat background. The theory is defined on mod on dz squared. So the background metric is not changing.
Background is e to the phi.
No, the background metric I would call as mod dz squared, but the physical metric is e to the phi.
Yes, so is it the theory of quantum gravity of the physical metric?
Okay, maybe you can call it theory of quantum gravity, but
No, but maybe you're doing classical, so I think maybe
Yeah.
it doesn't matter.
But even classically, is not imposing the equations of motion that follow.
No,
before
energy
we-
moment and tension is not zero.
I
yeah,
think so.
it's not zero. Yeah.
It's not zero.
Yeah.
That's what I want.
Yeah. Okay.
So T is 0, there's no T in the Lagrangian. It's just
No.
both the terms are curvature.
Team you of this
Of this
I think viewed as a conformity.
Yeah.
Yeah.
Meaning, if before fixing to this gauge, you
Yes.
computed all the Einstein equations, there would have been 2 more Einstein equations.
Mhm.
You're keeping only this one.
Z and Z bar parts of the Einstein equations also have to be satisfied if we treat it as a theory of gravity.
Okay.
Okay.
Okay, now I want to insert this into the path integral, insert this line defect into the path integral. So as you can see, the line defect is of the form exponential something. So this something will just modify the action. So this will source the action. So now I consider a sourced Liouville theory where m over 4 pi integral phi. So this is like I mean you could roughly say this is like a relevant deformation of the Liouville action because m is like a dimension full parameter. and this is integrated over the curve that describes L sigma. Okay. Okay, so now we want to find solutions to this sourced Liouville theory. So it's the solution satisfies this Liouville equation, and in addition they satisfy a gluing condition. Okay, so the way to construct such solutions is by gluing hyperbolic surfaces along sigma. So you take two hyperbolic surfaces and glue them along the defect. So to get some intuition, let's say I have a line defect along sigma, and then I'm gluing two discs along this line defect. So I can take one disc and then glue it along here, and glue to another disc along this line defect sigma. So that's
The point that the equation of motion is unaffected away from the defect.
it's unaffected away from the defect. So yeah.
And the gluing conditions are the usual Israel junction conditions?
Actually, they become the Israel junction condition for gravity, because this is not gravity, right?
Yeah, so what jumps?
Yeah. So I'll return. So this is just like a problem of like electrostatics or whatever. So the analog of the potential would be the Liouville field, which is continuous. So the phi is continuous, but the normal derivative, which is like the electric field, jumps.
But this is just similar to the metric is continuous and then the curvature.
Yeah, exactly. That's secretly why this becomes the Israel junction conditions in 3D
But
gravity.
Diksha saying if you word it in terms of the full 2D metric,
Then it would be like.
physical 2D metric.
Yeah. That's right. Yeah. So I agree, because
That solution might not satisfy energy momentum tensor equal to 0.
yeah. Okay.
This system is related to the 3D gravity
Yeah.
because this is somehow sitting inside the 3D gravity. Is that?
Yeah. This is like the 3D gravity.
So you're thinking of the 3D gravity as
This times an interval.
this times an interval. So
Yeah.
some hyperbolic manifold times.
Times hyperbolic surface times an interval, and somehow the theory of 3D gravity on that topology gets reduced to this Liouville CFT. That's how 3D is related to
I
Liouville.
can always do this. I can use some hyperbolic foliation of 3D gravity.
Yeah.
to do.
In fact, you don't even need like two boundaries, like because the argument that I said needed two boundaries. But you can also do a hyperbolic slicing of a single boundary geometry, like ADS3. In fact, so Liouville theory also governs single boundary solutions. Okay.
Parameterize the SL2 gauge fields, written SL2 gauge fields in terms of the
I see. Yeah.
And that 3D became 2D is somehow the fact that 3D gravity had no degrees of freedom. That it's all boundary degrees.
Yeah. That's right.
So it's just a gauge fixing of the 3D.
Yes.
Yeah,
You
that's
can
right.
fix and parameterize this E's in
Correct.
a particular way, then just we will just falls off.
In the gauge field like this.
In the gauge field, you take the Chern-Simons,
Yeah.
you gauge fix, you take A to this parameterize A in terms of a single scalar field. Scalar field on the boundary.
Okay. Okay, so the jump condition is nothing but the jump in the extrinsic curvatures. So the difference in extrinsic curvatures, like say above and below this defect, the jump is governed by the mass of the defect.
But now we're in 3D bulk.
No, this is like the two-dimensional extrinsic curvature of this surface.
2D extrinsic curvature viewed in physical.
Viewed in the exactly physical metric. Yeah. So, or you can rewrite this in terms of normal the jump in the normal derivative. So the normal derivative of the Liouville field jumps by an amount equal to 2m. I mean the signs are dependent on how you define delta. So just remember that the jump in the normal derivative is the mass of the defect.
And this is just to make sure this condition
Mhm.
is determined by requiring that this action gives rise to the right equation of motion.
Yeah, that's right.
The boundary terms.
Yeah, so these are like equations of motion. So you can check that when you vary this action with this condition, you get a well-defined action principle. Okay. So for our purposes, when we want to, so the strategy would be, okay, so what is the goal? So the goal is to compute correlators of L, correlators of the line defect L sigma, and the strategy is to do that by gluing hyperbolic surfaces along sigma. Okay, so there are two building blocks.
Immediate question: what if this Liouville theory was already defined on some curved?
Yeah, you could also define it on some curved background, but
Then what is the connection between this physical metric and that background metric? Is there any?
Just a shift of phi. Right?
yeah, that's a shift of the Liouville field, because any 2D metric is conformally flat. So if there was like another like phi naught, say that determines the background metric, then it causes a shift in the Liouville field.
But does this mean that this background physical metric that you obtained, I can also think of it as, so this is again the question that I asked earlier, ordinary Liouville without the defect, but now with this funny, with that background metric, with this physical metric being the background metric, or not?
I think background metric is fake in Liouville. Because phi is dynamical and you can just shift it away.
Yeah.
Right, because any background metric can be in the right gauge. It can be written as e to the power phi tilde.
Okay.
So just redefine it.
Okay, so the two building.
The background metric, however, this the background charge Q, that will come back into the action as Q times R hat times phi. Right now, only the stress tensor remembers that there is a Q.
Yeah.
But so you have to do that bit a little bit, because your action would
Correct.
explicitly have a new term.
Right. Yeah. So there's no. So okay. So there's another term that will show up as is pointed out, which is proportional to the Ricci scalar of the background metric. So because I'm working with the flat background, so that term doesn't show up. Yeah.
Can I think of the additive term itself as some background metric with constant R?
It's a little different way, because this one is a delta function around the equator, and that thing is a background charge all over.
Yeah,
Yeah.
Yeah.
It's a co-dimension.
It's
Yeah.
a 2D integral.
Yeah.
So it's R only localized on the equator sort of.
Yeah.
Yeah, but that's how it looks like that, right?
Yeah.
The background metric looks like that.
Yeah.
So that's why, I mean, this looks like this line operator looks like a theory defined on the background metric, which is that.
I see.
Which is this? Because if this is so, then
Okay.
the bulk solution will not make some shell or anything. It will just fill it out.
No. See, Liouville is auxiliary because like the real match is between CFT and gravity. So CFT, there are line defects that you insert on the sphere, and that will source the shell. Liouville is just being used as an auxiliary system to calculate the bulk. So it's not that the Liouville is sourcing the shell. Liouville doesn't have anything to do with
But
the
I
shell.
could ask what is happening. What is the dual? What is dual to this line operator?
There's no meaning of that because Liouville CFT is not dual to 3D gravity. It's not. It doesn't live on the boundary.
No, but you can ask what's the because it's a topological theory in the bulk.
Yeah.
You can ask do something to the Liouville, it does something to the bulk.
Yeah, I mean it
Not in the
changes.
sense of ADS-CFT.
Okay.
I mean just as a mathematical change of variables, right?
Yeah, I mean if you take the bulk with the topology of this kind of surface times an interval, then if you change the Liouville metric, of course the bulk changes. Yeah. Okay. So the two building blocks to compute these correlators are the disk and the annulus. So I just use these two surfaces to construct all the correlators, like any multi-point correlators by gluing, by appropriate gluing. Okay, so it's always convenient to work in the cylinder conformal frame because the Liouville field is sort of simpler. So in the cylinder conformal frame, the Liouville field on a disk takes this very simple form. So okay, so in the cylinder frame, the disk is mapped to a semi-infinite cylinder. So there's a y coordinate that runs along the cylinder, and the metric on the disk in this frame is mod dc squared by sin squared y. Okay. So the next is the annulus. So the annulus is a conformal to a finite cylinder. So this is just a hyperboloid, like a finite hyperbolic cylinder with some height and some width, and the metric on this cylinder, I can write it to be in this form, by cos squared rhy. So again, y coordinate is a coordinate that runs along the cylinder. So the cylinder has height pi over rh, and the length of this minimal geodesic around the waist of the cylinder is 2 pi rh. So the reason why I am calling it rh is because this becomes a radius of the black hole horizon in 3D gravity. So the size of the cylinder, the hyperbolic cylinder, is the radius, is the horizon radius.
Sorry, what are we trying to do when you say correlator of L sigma?
So let's say like to a 1-point function or 2-point function.
In some state.
Vacuum or thermal,
Okay.
on the torus. Yeah.
So are you going to compute just a classical Euclidean action
Correct.
with that metric?
Correct. That's all. Yeah. Okay, so let me give you an example so that you can understand how this gluing game works. So the simplest example is when you have this line defect on a sphere, just a single line defect inserted on a sphere. So I want to compute the 1-point function in vacuum by doing this gluing. So how do I do that? Let me take two disks and then put the defect at some radius. So these are hyperbolic disks, and I put them at some radius which is less than 1, and then what I do is I glue the unshaded portion. So I remove this portion and I remove this portion, and then I glue this to this across the trajectory, across the circle, across the defect. So what that will give me is a squash sphere.
How much squashing depends on the
The mass. So if it is very massive, then more squashing. Okay, so what is the Liouville metric for this? By working in the cylinder frame. So in the cylinder frame, how would this look like? It will look like something like this. Because each of these disks is mapped to a semi-infinite cylinder, and then those semi-infinite cylinders are joined along the trajectory of this line defect. So this is equivalent to this by conformal map. Okay, so what is the Liouville field? I can write the Liouville field in a split form, like let's say the defect is at y equal to 0. So this is y greater than 0 and this is y smaller than 0. And I know that the form of the hyperbolic metric on this semi-infinite cylinder is of this form. So now I'll just use this form to parameterize my Liouville field. So this is for y greater than 0 and minus 2 log sinh y a minus y for y less than 0. It's just this, like I have written this as e to the 5 mod dz squared, then I've taken the log and it's minus 2 log sinh, I mean there's a shift now.
So why is the Euclidean time on the cylinder frame?
There's no y is yeah. So you see that if a is greater than 0, then there is no longer a singularity. So for instance, if you look at this metric, it was singular at y equal to 0. That means at the boundary of the Poincare disk, we know the hyperbolic metric diverges. But I can cure that divergence this way, because if a is greater than 0 now, this part is not divergent and even this part is not divergent. So you can think of the line defect as sort of like curing the hyperbolic, the divergence of the hyperbolic metric.
And sorry, can I think of it this way, that if I couldn't make a sphere a solution.
Yeah, your sphere is not a solution, yes.
Just because integral r
Yeah, the topology on a sphere doesn't allow hyperbolic metric, but what I can do is I can backreact the sphere on the sphere by matter,
And then you can put
yeah.
it.
Yeah, so the thing is, like, if you are backreacting by point matter, you need at least 3 points, because a sphere with 3 marked points is hyperbolic. Whereas if you have a line defect, just you can put one defect. Yeah. Okay. So then, how do you determine A? So if I write it this way, it's trivially true that the Liouville field is continuous, right? Because at y equal to 0, it's the same. So now A is determined by using the jump condition, that the difference in the normal derivative at y equal to 0 would give me A. So so it turns out that A is half log m plus 2 divided by minus 2. So actually I have set the radius of the defect to 1, that's why you see, maybe you are worried about dimensions. So if you put back the radius, it will be mr, so that that is dimensionless. Okay, now you
Sorry, this E is the most general integration constant of the solution of the
Yeah.
Liouville equation.
yeah, with the symmetry, because there's a rotational symmetry, right? So the entire solution only can depend on y coordinate.
Yeah, but this becomes a ODE
Okay.
once you impose that symmetry.
Once I impose rotational symmetry, it becomes
Only one-
one.
one
Yeah,
constant.
there's only one constant.
So what happens at n equal to 2?
Yeah, so so then you end up with the divergence. That is expected because the sphere does not admit a metric, but now I'm backreacting by a matter. So the matter has to be sufficiently heavy to create a hyperbolic metric, and it is saying that the threshold to create a hyperbolic metric is m equal to 2. So there's a saddle only when m is greater than 2.
Just again about Gautam's question,
Yeah.
it becomes an ODE, but a second order ODE, right?
Yeah.
So how come
The second order ODE, the Liouville equation becomes a second order ODE, but there's a jump condition.
just local solution? Why aren't
Yeah.
there 2 integration constants?
No, there is.
Something imposed at y equal to plus or minus infinity.
Oh, I see.
Isn't there also regularity?
Matching at y equal to 0 will get rid of 1.
Yeah, 1, but
That's the
then
jump.
y 1 should remain there.
So there are 2 junction conditions, right? One is continuity and then the jump in the normal derivative.
So after
Oh,
y
I
equal to
see.
0, A remains,
Got
it.
when A is fixed.
Yeah.
Yeah. So the 2 A's are the same just by continuity.
Yeah.
No, but I just in one part,
Uh-huh.
why aren't there 2 constants?
Each solution could have, so is it like,
Regularity.
yeah, is it like by plus A is, I forget now what the secondary.
No, sorry, it's like a Liouville solution on the entire thing, right? It's it has only 2 parameters. So I mean, I don't think you should take the Liouville solution in 2 different parts.
See, on the northern hemisphere as well as on the southern hemisphere,
Yeah.
you were solving just the Liouville equation,
Right.
which is a second order equation.
No, but you should think that I'm solving the Liouville equation on the sphere.
Never mind.
Yeah.
No.
Locally,
Let's say locally.
Yeah,
Locally, I'm solving first on the north and then on the south,
Uh-huh.
and then I'm matching them.
Okay.
Forget
True.
the matching.
True. Okay.
So I'm solving a second order differential equation in the north.
Uh huh.
Okay. Then I should have 2 integration constants.
I think it's like
The matching might make that, I still don't understand.
but isn't it regularity usually
There's
areas
some
of
regularity at some point.
At infinity is
Regularity at infinity, I guess.
I
Yeah.
think that's why something is imposed at
At the
y
north
equal
pole,
to
at
plus
the north
minus
pole,
infinity.
at the north pole. Okay, maybe.
Yeah, north pole and south pole.
Yeah. Right. It has to be regular.
Yeah.
Right. Yeah. Thanks. Okay.
Is there a simple way to understand this m equal to 2? Because for points you can understand this by just drawing triangles and requiring.
Yeah. So if you think of this as points,
Yeah.
some of them, some of the conical deficit angles around each point is marked.
Okay.
Yeah.
I think if you look at the normalized formula, then M is literally the curvature. So as long as whatever your curvature created by that C, it has to nullify the -2 that is already there,
Mhm.
and then only you can have that answer.
Do we have a seminar organizer or this is an infinite time seminar? No, just
Yeah. Sorry. You can tell me when I should end.
Should impose some regularity.
Because on information loss.
Yeah. Stop when it is natural to
Yeah.
stop.
conditions are different.
Okay, yeah. So I guess I'll stop when I discuss the 1-point function, I guess. Like the calculation, the value of the 1-point function.
So you get the value by putting this
Into the Liouville action. Yeah, that's all. So that's why I will skip all the details and say the final answer. So the Liouville action is, oh sorry, let me first give some, okay, if you compute the stress tensor of this theory in this, so it's called, the Liouville stress tensor has this formula. So it naturally takes this form. It's uniform everywhere except that there is some energy density on the defect. So it's a delta function with size m on the defect, but it's uniform everywhere. I mean, all these are in some rescaled units. That's why you see like 1/4 and stuff. So, yeah.
Just one comment.
Yeah.
If we inserted operators at the north and south pole,
Yeah.
then they would have activated Gaussian
Yes.
additional Gaussian solution.
Yeah. I mean, actually this is an example of that, right? There are operators at the north and south pole. Yeah. So what that would do is like that would do something like this. That will make this like, something like this. Yeah. Okay. I don't know.
And that would activate the second solution.
Yeah, but that is like changing the asymptotics. Okay, I guess maybe I forgot to say that the asymptotics are fixed, so that's why you get rid of those solutions.
Asymptotics are infinity.
Yeah. So because if you take if you take y large, the asymptotics is phi goes to minus 2y. Whereas if you introduce a conical defect at infinity, it goes to like minus 2 times 1 minus 2 eta y, where eta is like the deficit angle.
And
So
you can see this y phi equals minus 2y by going back to the disk frame. Right?
yeah, going back to the disk
Asking it to
frame.
be
Yeah.
regular,
Yeah.
on that side.
Yeah.
And yeah.
Okay. So this is the 1-point function by calculating the Liouville action. So the Liouville action is m plus 2 times log m plus 2 minus half m minus 2 times log m minus 2. So this is so that means the 1-point function in the semi-classical limit. Let me now put back the radius. So the radius of the defect is r. So it's mr minus 2 times mr over 2 minus 1 times mr plus 2 times to the power mr over 2 plus 1 to the c over 3. C over 6, sorry. So this is the g function. So the g function is a function of m times r.
What is the first bracket here? 2?
2e exponent.
Exponent.
Yeah. Okay, so let me explain a little bit about some nice properties of this function. So just like in compact CFTs, you can define like the analog of the defect entropy, which is defined in this way. And this function actually changes monotonically. So you can just plug this here and compute this defect entropy. And so the way to go to the IR is by cranking up m times r. So this, as you increase m times r, you are going into the IR. So so in this process, so under this process of cranking up m times r, s decreases monotonically.
Somehow I forgot what R was.
R is the radius of the cylinder. I mean in this part I just set R to 1. I then put back R at the end.
Radius.
Yeah. Radius of the defect. Yeah.
Oh, I see.
Mm-hmm.
I see.
Okay. So this function decreases monotonically from the UV to the IR.
This is this Cardy's reformulation of Zamolodchikov's theorem, right?
Well, all that applies for compact CFTs. I'm just like you can say that this is like a definition for this such non-compact Liouville CFTs. Yeah.
And also it's a defect quantity.
It's a defect G function.
Defect CFT C theorem.
Yeah. So there's like an analogous thing called a boundary G function when you have boundaries, but this is like a defect G function.
And this calculation was for large C, right?
Large C. Yeah, it's an interesting open question, like how to do this calculation exactly in C. I don't know. Maybe someone has ideas here.
Sorry, a trivial question.
Yeah.
Large C means large background charge also? No,
Background charge is B plus 1 over B, so B going to 0, so 1 over B blows up, so background charge blows up. Yeah.
So I thought that this del square phi piece in the stress tensor, that multiplies Q?
Yes, there's some also rescaling by B's.
Also you are, okay.
Yeah, there's all sort of rescaling. Yeah. This is not the quantum stress tensor, this is a classical stress tensor, so there's some rescaling by B's. Okay, so now let me give you a very quick argument for why in the IR this defect becomes conformal. So this was a non-conformal defect because of the presence of a mass, but when you go to the IR it becomes conformal. So to see that, let me work in the planar limit. So I was working on the cylinder, now I am just taking the planar limit. So the defect now is along the real axis. It's an infinite line defect along the real axis. And the Liouville solution takes a much simpler form now. It's minus log y plus 2 over m and minus 2 log 2 over m minus y for y greater than 0 and for y less than 0.
So it was not a conformal defect because phi had the thing you integrated over did not have dimension 1.
Yeah, because the mass was dimension full, right?
Mass was dimension full. And just from the point of view of the well sheet CFT, the if it was like a dimension 1 operator and you integrated it, that would be marginal.
Yeah. Like for instance, as you pointed out, like if you integrate e to the phi, so that is expected to be marginal.
And also phi is not a nice operator.
Phi is not like a scalar. Phi is not scalar. Yeah.
It's not a del phi or anything.
Yeah. Okay, so this is the Liouville field. So you see that there is a distance scale here set by the inverse mass of the defect. So what this is saying is that if you are in a window which is like of a size 1 over m, and when you are very close to the defect, so you can ignore this term and just keep the 1 over m term. So which means that the correlations, if you put a probe here, so the correlations of the probe will be constant when you are like well within this distance scale. But then if you go very far away from as compared to this characteristic size of 1 over m, so you can ignore this part now, and so the correlation is like the usual what you expect from conformal field theory. Like if you have a line, if you have a conformal defect here, this is the correlation that you would expect from CFT. So what is happening is that if you take m going to infinity, so these two half planes which were merged along the defect will split. So it's as if like I'm going back to this picture, because the resulting metric that I wrote here is just the metric on two half planes. It's just the Poincare metric on two half planes. So that means the defect is now very heavy, that it doesn't allow any transmission across from here to here. So no energy gets transmitted through this defect. So it's like a hard wall. So all the energy gets reflected away. So it becomes perfectly reflecting.
These integration constants are now different in upper and lower half plane.
No, it's the same.
A constant.
It's 2 over m.
It's like the gluing is happening at infinity. Right?
Yeah.
Gluing is happening all the way.
No, the gluing is happening only along the defect. But it's just that the defect becomes very heavy in that limit. It becomes like impermeable. So
I thought the mass of the defect was roughly where you glued.
The defect is going off to infinity, right?
Yeah.
I see.
I think that makes sense. Everyone can understand that. It's going off to infinity.
Because you're just rescaling.
Yeah.
You've
That's
got an
right.
area space and you're rescaling. So
Right.
that's sending it off to infinity.
Right.
Any finite thing goes to
Got it.
Okay, I think this is a good point to conclude. Yeah, thanks.
Good
could you just once remind me what this one-point function was supposed to map to in the statistical sense for CFTs?
Yeah. So the one-point function was supposed to govern the statistics of the one-point function of the CFT defect. So this computes the variance. So the variance of the CFT defect is governed by the one-point function of the Liouville defect.
I see. So this calculation is roughly like a wormhole.
Yeah, this is roughly a wormhole calculation. Yeah.
And in that wormhole, if I take that wormhole and slice it in some time direction or something, and reduce the basically ADS3 equations to a two-dimensional.
It becomes a Liouville
then
equation.
these are these.
The Liouville, yeah, it becomes a Liouville
So that's
equation.
the correspondence.
Yeah, that's the correspondence.
But once you double, once you put two lines.
Yeah, you have to do the double.
Yeah,
There are two boundaries. Yeah.
More questions? If not, let's thank Jeevan again for.